Hey everybody, so we're going to start today with a little demonstration. As you can see, there's a little compass here, and I have a wire next to it, and the end of the wire I'm going to touch a battery. Now, you might not think a whole lot of this, but it's actually kind of a big deal. If I run, this is a DC battery, current through a wire, and I have a compass nearby, it moves. Remember, the only thing that can make a compass move is a magnetic field. Now you'll notice the red arrow is pointing when I hit it towards the right. I'm going to change the battery and make it go the other way, the current, and you're going to see, notice that red arrow is going to the left. So, minor little thing, but in history, the first person to do this, I'm going to just bring up my iPad here. So you can see a little picture of him, was a guy named Hans Christian Ørsted. All right, so Ørsted is credited, and you can just read it here. Look, it says Ørsted was a Danish physicist and chemist who discovered that electric currents create magnetic fields. So it was, if you look at his dates, he was alive 1777 to 1851. That was a long time ago. So he was one of the first people who noticed that running electricity causes a magnetic field. And how did he detect it? Probably with a little compass, not much different than this. I'm going to show you a different one. Of course, I might have some noise here in a minute. I apologize. So I'm going to bring in a wire and 4 compasses. I'm going to move some other things out of the way, and I'm going to connect this wire. I'll move it a little bit more this way. You can see the wire is not perfectly vertical, but that's okay. I'm going to connect it also to the battery instead of having one and next and being like above it. I know this should look straight like this, but just so you can see, I'm going to connect to the battery for just a couple seconds. Oh, changed my lighting. Sorry about that. That's where I want to be. And notice what happens to the compasses. Hopefully you can see that all the red arrows are going around the wire in a circle. As a matter of fact, it would be counterclockwise. I'm going to change the battery direction and see what happens. See, they went back to normal. And now if you take a look at them, the red arrows, loosen up there, buddy, it's going around clockwise. So not only did we find out that running electric current will make a magnetic field, and the way we detect it is with compasses, but we also know that it goes in the shape of a circle. Okay, let's pull this out of the side for a second. And we're going to get into the notes. Let me zoom a little bit less. So let's just make a little shout to Ørsted, okay, because this essentially is what his body of work was about, making electric fields making magnetic fields from electricity. All right, so let's talk about the formula. The magnetic field around a wire is going to be calculated as K, which is a constant, I, which is the current, and the distance you are away from it. Now I didn't use a very giant battery, so I didn't make a really strong magnetic field, but the farther away you would go, the weaker it would get. So let's do a quick calculation here. And I have my calculator. Okay, calculate the magnetic field, that means B. Literally, I looked this up recently, that there was a list of Maxwell, there was a scientist named Maxwell, and he made a list of different kinds of, I guess, magnetic effects, and literally B was second in the list, and it had to do with magnetism. So that's why the B. I never knew that for a long time. All right, so what is the B? Well, we're going to have 2 times 10 to the negative 7th, 5 amps over 0.01 meter. Well, let's see what that looks like. Let's grab a calculator. Turn it on, clear, 2 second EE negative 7 times 5 divided by 0.01. So 1 times 10 to the -4th Teslas. Now, the Earth has a magnetic field. Okay, we're just gonna make a little note of this. On average, because we know it's stronger at the poles, is roughly what we call 50 microteslas, or 5 times 10 to the -5th Teslas. That is what Earth is. So this is stronger. That compass moved away from the Earth's magnetic field because the current in the wire forced it to. The math isn't so hard on these. The directions may be, because we can talk two ways. One, we can talk about current flow, or we can talk about electron flow. And we have hand rules. Yay for hand rules. They're like the torture of every physics student. So this is a three-dimensional drawing. So imagine that you have a wire, and I have to remember, how does the magnetic field go in the circle, clockwise or counterclockwise? Well, here's the wire. You take for current, you use your right hand. So here's my wire. I make my thumb go the direction of the current, in this case maybe up, and I curl my fingers, and that makes the direction. So this would be a directional drawing. That gets a little hard to do 3D. So they had to come up with a different way of looking at it, saying instead of looking at the length of the wire, not that we won't, we're going to look at the ends of the wire. Electrons or current, let's say current's going to come towards you or away from you. So when we look at the end of a wire, straight down it, we're talking about current going down or up. And somebody came up with the idea of using an arrow. If an arrow was coming at you, you would see the point. If an arrow was going away from you, you would see the tail. So moving away from you, we use an X, which was like a tail of an arrow, even though I know there's only 3 feathers. And if current is moving towards you, we use a dot. Now we use the same thing if it's electrons, but we have to use our left hand. So the way this works is we look at this not from the length perspective, but from the top perspective. So we're going to use our right hand because we're talking current. X means current is going away from you. So on a piece of paper, and you need to practice this, first of all, it's kind of like a hitchhiker. Your hand looks like this. X means that they're going away. That means point your thumb away. And you see that my fingers are curling? You're going to draw arrows. So first of all, we're going to make a circle. Outside of that, don't draw on it. And then X means, think of your fingers as little pointers. And so it's going to go this direction, which is clockwise. If we were looking at the end of the wire and the electrons are coming at us, again, we're going to kind of do this thing. First, let's make a circle. Just make a circle outside of it. You point your thumb up, and if you notice, my fingers are pointing this way, and that would be the direction of the arrows. Okay, so this one is going to go counterclockwise, this one is going to go clockwise. That's for current. If by chance we start talking about electrons, I'm going to move this up a little bit, we would use our left hand, and that's going to come in. We're going to stick mostly to current, but there's definitely going to be times when we have a talk about electrons. So rule number 1 is for circular fields around wires. If we are using electron flow, we use our left hand. If we talk current flow, we talk our right hand. The rule is your thumb points the direction of the flow, and this is a 2-dimensional way to represent something that's really a 3-dimensional. And then our fingers, they curl, and that curling matches the arrows. All right, we'll be changing the shape of our wire next time. Bye now.